Hi, here we will see how we get the pulsating DC, and this pulsating DC is given to a comparator which is compared against this fixed voltage, and that delivers this kind of pulses which are called zero cross pulses or zero detection, zero voltage pulses. This green is the zero voltage pulses, this yellow is the pulsating DC, and this orange is the fixed DC. And we know we get sawtooth voltage when we compare it, when we pass it through a transistor switching, and that sawtooth voltage is again compared against certain fixed voltage which generates this kind of output pulses, and ultimately if it is a DC, that means two diodes and two SCRs, then we get from the AC this kind of DC. We will see now while we simulate, the idea will be clear. Now see, this is the pulsating DC, this is the fixed DC, so we get this kind of pulses, and then based on which the sawtooth voltage is generated, and this sawtooth voltage is compared against this voltage. Now if I change this and then the width, on time width is this, and this is the delayed angle. Now if we change the time here, the fixed voltage here, you see this width is increasing, this width has increased. Now if I further see, the further width will be increased here, further we find further increase. The more we, that means delay time is decreasing, my power delivery is becoming more and more. Now see the waveform, I can see it is more than 90%, more than 50%. Now further, now further, now further. Now you find I get full DC. I get full DC. Remember, this pulsating DC is only a control voltage, is a controlled DC, is a controlled, it's coming from a control circuit, whereas this is my output, which is the main power which is converted from AC to DC, and this is how it is achieved. Now see, this is the level, and as I go on, this blue line is the level. As I go on changing the level, now I have changed the level, you see there is a little delay here, and based on that little delay we get little less power from the full rectified circuit. Now little I get further delayed, and then you can find the power is further less here. Now further delayed, the power goes on reducing, this DC power is going on reducing. Further delay, see only this much of power from here to here, from here to here it is not conducting. Further, just like this, and you can see this width is going on increasing, that means this time, the delay time is going on increasing. Further, I can see this level is going up in the process, this is becoming narrower and narrower, that means this is getting delayed from the zero, this is the zero line. Further, you see how much power, the power is becoming very little now. Now almost very little power here, because it is heavily delayed, almost delayed by 7-8 milliseconds, so you get very little power. If I delay further, there is no power. This green is the AC input and DC output is not available. So this is how we achieve the power control, DC control. Now let's go back again. See, we get little power. This is the DC. The level is here, and this is slowly, if I now slowly bring it down so that this width will go on increasing, that means the delay time will go on decreasing and the power will go on increasing. Now let's see again. I have reduced this level further reduced, so this becomes wider, further reduced, this becomes again further wider, and that is how the power delivery goes on increasing. The lower it falls, the wider this becomes, the nearer to the zero it becomes, the higher the power it becomes. This is how the DC is controlled. So what in practice we do, that this change, this level change which is happening, is actually controlled from a feedback circuit, and that feedback maintains this at a particular level. If the voltage goes on increasing, this level will go on rising. When this goes on rising, this will be narrow. This will be narrow, and this will be getting more delayed. More delayed, there will be less power. So it will again maintain the voltage. If the voltage falls, this feedback voltage will fall here. That means it falls means the voltage will increase here. So this is how the arrangement is made in an analog circuit for controlling DC power. Right? Now if we go over to the circuit, we can see all of them in the circuit. Let me remove these CROs. We have the comparator here, and this comparator is with a fixed voltage, and the pulsating voltage is coming from a bridge rectifier here. So what I get here is zero cross detection. This is what I get here is, this is compared against 0.6 volts, and in the process I get zero cross detection. So these are zero cross detections, right? And after that zero cross detection, it is being fed to the transistor, and there is a capacitor here with charging and discharging takes place. And that charging and discharging takes place by this, and then we have the output LED which is fed this much of on time and this much of off time, and that those two LEDs are connected in series, and ultimately they are feeding two SCRs and two diodes which are in the bridge configuration, being fed from AC supply. And that is how it works.